Yeah, check, check. Okay. 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 All right. So welcome back. Going to change gears a bit here and talk about this sampler called MC. It's a Python package. It's pretty easy to use. So it's a nice way to get started on using MCMC if you've never done it before. For a certain class of problems, it's really effective. I'm going to try to I'm on the paper, so I can't be entirely fair, but I'll try to give you a fair assessment of when it might be the right tool for the job. It's too bad that Brendan's not here right now because he has very strong opinions that it's not the right tool for any job. Oh, he is here. There he is. He's just hiding. Okay, but so please, speak up because we may as well make this informative and as truthy as we can, right? Yeah. Okay, so all right, so let's start with a little bit of motivation. Brendan already gave you the basic Metropolis Hastings. You've probably maybe seen this to death. The basic loop is you're moving one particle through a parameter space. And the basic loop is choose a new place to jump, see whether the likelihood and prior are better there or not. If they're better, go there. If they're not, sometimes go there. So you can think of it in some ways as like a random walk, hill climbing sort of thing that sometimes chooses to go downhill. So you take a random step. If it's uphill, you go that direction. If it's downhill, you maybe go that direction. And this balance between climbing and descending allows the particle to explore the space. Okay, so two kind of disadvantages up front are that you have to give it this proposal distribution. So if you're at a particular point, a distribution of places to jump next. Now, in principle, well, in practice, that can be really easy to do. It can also be really easy to do badly. And common practice is often pretty bad. And I'll sort of show you a little bit about that. And another thing, just from a very practical perspective, is this is very much a single-threaded kind of process. I mean, you're moving one particle around the space, and it's entirely sequential. There are more sophisticated ways of doing things in parallel and making sense of what the parallel chains mean. I should also say that I'm not really a very sophisticated Markov chain user, so honestly, I'm not entirely sure why I'm giving this lecture, but here we are. Maybe that's good because I don't know everything. So, the front row should please do speak up because we may as well entertain and inform. Okay, so here's a very simple two-dimensional parameter space. It's a covariate Gaussian, right? So bright parts are high probability space. So imagine that you've got a Metropolis Hastings and you're initializing it way over here in the tails. And this circle is showing your proposal distribution. So it's saying you can jump, from that position, you can jump uniformly in any direction. Now, you know that you can see that this parameter space doesn't have that property, right? Like it's really the two variables are, the two parameter directions are really covariate. So really, you should tell it that it's better to jump along this line than across this line. But people often do just say jump uniformly in any direction. Okay, so the first couple of steps might, the first step might go there. That's clearly much further up the hill, like it's in a brighter, it's currently it's so dark that you can't see how bad the probability is there, but it's still getting better. There's another one that is probably not too bad. That one jumped downhill and it was rejected. So the red dots, I'll show it. Red dots indicate a rejected step. And then, you know, essentially you move up onto the plateau. There was a proposal to jump right off, to jump right down off the hill into the ocean. That step was rejected. And then, you know, essentially it just wanders around, exploring the space. So after 40 steps, it sort of explored the bottom part of this ellipse. Surprisingly, that went off and wandered around down in the south side of the island. But then, you know, after given enough time, it essentially gets to explore this whole, the likely parts of this parameter space. Okay, so, you know, as I said already, you're moving a single particle around the space. The moves are based on a proposal distribution that you have to give it. And I guess one of the main problems is if this isn't very well specified, if you don't give it a good proposal distribution, then things can go badly. So a classic example is if the proposal distribution is too narrow, then essentially most steps will be accepted, and then it just takes a long time to get anywhere to explore the entirety of the space. So yeah, you can imagine that if you're taking very tiny steps and testing whether that is better or worse, few tiny steps are going to be very much worse. So many of those will be accepted. And it also just takes you a really long time to get anywhere if you take tiny steps. So that means it can take the particle a really long time to explore the space, which means that you just have to run the sampler for a very long time. Or you get tired of waiting for it to finish and you say, all right, I need to publish my paper already, and you can publish results that are wrong because you haven't explored the entire space. Okay, on the other hand, too big of steps means that you too often are in a good part of the parameter space and take a big step that leads you to some terrible part of parameter space. You reject it, but then that means that you're not going anywhere because it's, again, too hard to move anywhere that's as good as where you already are. So I'm going to go back a slide just a second. And if you look here, you can see that there are the blue steps that were accepted and the red steps that were rejected. Right? And you can see that in this example, there may be 2/3 blue and 1/3 red. That's kind of a visual version of the acceptance ratio, it's called, which is the fraction of steps that were accepted. And that's one thing that people usually use to determine whether the MC is the Markov chain is working well. So if you, yeah. Not. So that they were rejected. Right. I showed it at the beginning. So this was using the same step size for this entire thing. Yeah. So I'm not saying this is smart, but this is something that you might see people do. Yes, that's right. Right, so the red points are not included in the sampling, only the blue points are. Pardon? Yeah. Okay, so basically, and I showed you a two-dimensional example here, right? And so if you wanted to specify that instead of giving a single uniform step size in any direction, if you wanted to give a covariance matrix, then that would be what 3 parameters, right? And whereas in a higher dimensional problem, you have to give sort of d squared. Like if you're working in a 6-dimensional space, you have to give it like almost 6 squared parameters to describe how to jump through the space. So this quickly gets out of hand, and people end up doing things that lead to bad results. So MC is one alternative to this kind of sampling. And the idea here is, instead of using a single particle and moving it around the space, we're going to use a whole group of particles at once. And use the covariance of those particles as the distribution, as the proposal. So instead of walking a single one that knows nothing about anything else, we're going to walk a group and move according to the positions of everyone in the group. All right, so the nice thing about this is that you don't have to give it a proposal distribution. That just happens automatically. And basically, the algorithm for this one is that for each walker, so this group of particles, each one of those is called a walker. And the algorithm is for each, when you're making a move, choose one other person in the group and move according to the line connecting you in parameter space. So I have a picture of that, I think. Okay. If I'm there and you're there, this is the distribution that's used. So it can basically step like from its current position to halfway to where the other particle is, or twice as far in the opposite direction. And so now this is the same a zoom in of that same elliptical parameter space. And now instead of having a single dot that we're going to move around, there's this scattering of blue dots. And here I'm showing, let's see, I'm going to get, oh no, he's using the laser. So for this one, I'm moving this particle, or this walker. It's selected this one randomly as the other one it's going to use, and it's going to draw a sample randomly along this line. So in that case, it draws one that's fairly nearby, and that one is accepted. So then it moves on to the next particle, chooses a line along which to sample something from it. This one is a step downhill and is rejected. It just goes on and on like this. So now, so here I've drawn a whole bunch of these, a sampling of like an example of all the different places you could end up by doing this proposal. So you can see that it's basically it's centered on where they all are, and it's sort of automatically the same size as the current distribution, but it has a little bit of spread. And after the first, so this plot is getting a little bit busy now, but I've now shown the ones that were accepted in green and the ones that were rejected in red. And you can, so the starting point was the blue circle, blue ellipse, and the position after the first step was this green ellipse. So you can see that it's basically moved a little bit uphill toward the good part of the parameter space, which is over there. Okay, so then going back to this sort of view of it, after a few steps, you can see that it sort of starts to move over in that direction. And the blue circle is showing the covariance of the walkers. So that, basically the current estimate of what the variance is. And you can see that after a few steps, it basically finds the peak and also has a good estimate of what the shape of the peak is. So that means that it's now going to be making proposals that you move along this area of high probability rather than taking jumps off of it. So I guess that's sort of the core of the idea, or like the core of the picture of why this might work. Yeah. Sure. Okay, so say we've got 4 particles. At each step, we're going to move each of them. So each particle chooses one other particle at random. So say it chooses this one, and it's now going to jump along this line with the distribution that sort of looks like that, right? Pardon me? Yeah, this one is always the same. It's an adjustable parameter that nobody ever adjusts. The default sort of seems to work well enough that. So it can. So this guy can now end up here, 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 here. Now other places he could have ended up, I could have chosen this guy and jumped along. Oops, sorry, jumped along this line, so he could end up here, 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 or along here, 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 here. And then you repeat that for each particle for each step. Sorry, I didn't finish the algorithm. And then you make the same decision as in Metropolis Hastings. Is this better or worse? Accepted if it's better, accepted if it's worse by drawing a random in comparison to a random uniform. I'm afraid I don't know. Neither do I. Yes, that's right. Yes, it's to allow them to. It's allow them to. To allow them to grow quickly. So let me tell you give you a good reason why you need that. So common advice is to initialize by choosing as good a place as you know about in the parameter space and putting them in the walkers in a small ball around that place. So they often start out in fairly close together, and this lets them kind of extrapolate and like bloom out to get to be the right size. It's a choice, but often. So if you start from, if they start close together and are allowed to grow out to find the good part of the parameter space, then that may work better than, it's certainly easier to climb uphill. Like if they're on the edge of a mountain, it's easier to climb uphill being in a small ball, rather than if you spread them all around the space. So imagine we have this parameter space like I drew before, and you spread them all around. It might take a while before one of them actually chooses to sample along this direction and in a good spot along it. Yeah. So All right, you found the first real, or at least one serious problem with this method. It really only works well for unimodal distributions. It doesn't, if there are lots of peaks, it doesn't really work very well. It's pretty serious. Yeah, I mean, yeah. Yeah, I suppose, or restart many times, you know, and see if you find the same peak every time. Well, yes, right. I mean, knowing that there's a problem and solving the problem are different things. Yeah. No, I mean, it's a serious problem. Oh, you mean this shape, the one that where it sort of drops off like that? I can't really explain it in any kind of technical detail other than to say that it's easy to, yeah, you can make it longer or shorter. Maybe it, so here, let me go to the next page. So imagine that you're in a one-dimensional parameter space that has two peaks, right? And imagine that the walkers are, well, this might not be a good, let me put this one further out, right? And imagine that your walkers are all here in the good part of the parameter space. Now, in order to get way over there, you know, they're going to, their variant, their standard deviation is something like that. So in order to get way over there, you're going to have to take a jump of many sigma and find a narrow peak within that. maybe we should, I should have like a list of pluses and minuses, but no, we can do that for homework or something. What was I going to say? Oh yeah, so let me tell you about one other feature or buzzword or whatever you want to call it about this method, which is that it's affine invariant. Affine invariant, which just means that if you scaled or sheared the parameter space, then the behavior is exactly the same. So, like, let's say you're, again, in an XY sort of parameter space, but now, say, because of the way you read data off the instrument or something, Y goes from 0 to 1,000, and X goes from 0 to 1. In standard, like, Metropolis Hastings, you would probably have to do something to handle that. Like, you'd have to do something different, like use a proposal distribution that's allowed to take bigger steps in Y than in X. Whereas in MC, it doesn't, you don't need to do anything special, it just works automatically. That's a kind of nice feature. Yeah, so with multiple, right, this method is nicer. So the name of this thing does not work very well in spoken language. It works better in written language. So I apologize for any confusion. See, I'm on the paper, and but I claim that my main contribution is naming it. So I guess we're even downplaying that contribution at this point. Yes. In C. I don't. I'll try to do that. I'll try to do it. So here I was trying to come up with a parameter space that I thought would break in C, where Metropolis Hastings would be fine. But it actually didn't turn out that way. So I don't know, intuition is hard. So this is a parameter space that has sort of two modes, right? It's got sort of a good place on the top and a good place on the bottom and a bridge in between them, so it's fairly easy to get between them. So this is standard Metropolis Hastings running for 500 samples, and it's just going along doing its thing down on the bottom here. After a while, after a few thousand samples, it's kind of moving back and forth. And then eventually it finds, like, rediscovers this bridge, walks up to the top, explores there for a while, and then comes back down again. And over time, it sort of swings back and forth between these two sides. And then after 50,000 samples, this is what it's accumulated. This is its approximation to that parameter space. You can see that it has some mass everywhere that it's supposed to, but it hasn't really done the job of, like, balancing between the two sides that are supposed to be equal probability. And partly you can think of that, the problem there is that to get from one to the other, I had to walk through this bridge. And the balance between those two, how much time it spends on the two sides, is not determined really by how many samples, it's by how many times it can cross that bridge. Which here so this is sort of this is a picture of where that particle was over time, like, so in terms of number of samples. And you can see it sort of jumping from the bottom, it walks over the bridge, spends a little bit of time on the top, comes back down, and sort of toggles between these two states. So, you know, it does a fair job, but it's kind of not. I was hoping for more, honestly. But that's kind of this is a kind of classic problem with exploring multimodal parameter spaces. In order to get from one to the other, you know, take this example. If you had to get from this peak to this peak, you'd have to take a bunch of steps that are all going downhill, right, before you get into the valley, and then you can start taking uphill steps again. So for each of those downhill steps, it has to accept a downhill step, even though it's worse. So, it becomes sort of lower and lower probability that can ever make that, jump across that bridge, as this. If this is a very long valley, then it's basically impossible to move between the two peaks. Okay, so, what happened to my? Yeah, that's my hope. Although it appears my computer's not cooperating. Great. It's just gone blank, but yeah, guess it failed. Okay, for some reason I can get there coming from the other, starting from the end. One bad page in the PDF or something weird. Okay, so here's INSEE doing the same thing. I'm trying to pronounce it like New Zealandish. Nah, you're good, mate. Here it is, wandering along. Here are the walkers going after a bunch of steps. And strangely enough, it basically decides to keep. So at every step, it's got walkers in both the top branch and the bottom branch, and sometimes in the middle branch. I was pretty surprised to see this, actually. I thought it would totally break it. I thought it would do the same thing as Metropolis Hastings did, except never move between the branches. And yet, it seems to do this fairly consistently, that it basically ends up having some walkers in the bottom, some in the top, and some in the middle, and the ability to jump between them. And then at the end, it's actually come out with a pretty decent sampling. Like, it's got basically balance between the top and the bottom. Now, one thing I'll point out is this acceptance. I wrote out the acceptance ratio, like, so the fraction of jumps that were accepted. And that's, I don't know what, like, I don't know what's going on out in the hallway there, but I'm not worried. I don't know, what kind of acceptance ratio makes you happy, Brendan? 50% or like 70%? Or what do you want? Okay, so that's actually not as bad as I thought. And I suppose... Okay. So, and now you can sort of imagine that this is not... this worked, I thought, surprisingly well for this case, and I can tell you at least how it would get worse and worse as the situation got worse. So in this example, it had walkers in the top and the bottom, right? And remember that at each step, each walker is going to choose one other walker and sample along the line between them. So if one in the bottom chooses another one in the bottom, then it's basically jumping along this line in the bottom. So that jump is likely to be a reasonably good probability, and it's pretty likely to be accepted. On the other hand, every time that if a walker in the bottom chooses one in the top, it's going to sample along this line, and there's almost no place on that line that's good, right? So you can see that, like, if there is about 50-50, then at least half the time it's going to choose a proposal that's just stupid. And if instead of 2, if you had 3 forks or 4 or, a whole bunch of different modes in this parameter space, then you could see that the situation got worse and worse. So I wasn't able to break it here, but I can tell you how to break it. It obeys detailed balance, so it's legal. Okay, so then looking at the tracks over time, that sort of shows what we already saw, that basically the entire time it's got some particles in the top, some in the bottom, and some in the middle. Okay, right, that's just showing them side by side. We've already seen that. So I said one benefit of this code is that it's pretty easy to use. So I'm going to show you code for a second. I'm not as bold as Brendan. I'm not doing live coding. I'm doing a pre-cooked demo coding. So apologies. Okay, so where's my? Oh, it's me. Oh. Okay, so boring stuff except for the import MC line. I mean, MC. Pardon me? Oh, maybe. Is that working better? Okay. All right, so basically the ingredients you need are, I'll show you, this is the code for the tuning fork. The thing you have to write that's the most challenging usually is this log prob function. So it gets, you're told where you are in the parameter space, and you have to return the logarithm of the probability at that point. So that's evaluating your likelihood and prior at a given parameter setting. So, for the case of the Comet Holmes thing, it would be proposing an orbit for the comet, and my likelihood code would have to do the integration along the curve and so on. So this is usually like where the work is, and this is the part that's specific to your problem. And okay, so this is the tuning fork one. It's basically just a Gaussian, and the shape of the two branches is this arctan, and if it's I'm confused. Oh yeah, okay. If you're to the left of that fork part, then it just returns a single Gaussian. If you're to the right of the fork, it returns half and half for the upper and lower branches. So it's a really simple log prob. And then as far as actually, this is just boring code. Spray atom. Sorry, this is not very compelling. So as far as actually running, like loading the MC library, building the sampler, and so on, this is sort of what it looks like. Okay, so initializing the sampler. Here, I'm just using a single standard deviation. So I'm going to say there's a little built-in utility that says I want to start at a given point with a given standard deviation. So, just draw a bunch of samples within that ball to be the initial points for the walkers. You have to give it some initialization. have to tell it where to start. Yeah, there's, you know. Pardon me? So P0 is the center, sigmas are the standard deviations. Sorry. Oh, yeah. Not sure. I'm not sure if there are any other built-in ones, because it's hard to describe other essentially you just have to give it a place to start. And that's basically common to any Markov chain method. So, okay, and then a plot. Here's actually creating the sampler. So it's called an ensemble sampler. You have to tell it how many walkers and how many dimensions, and also give it your log probability function. And then basically, actually calling it, it just involves running sampler.run mcmc. You have to tell it the current position and how many steps you want to take, and then there's some handling of random numbers. And it returns a new position in parameter space after having taken that number of steps, a new log probability, and a new random number tracking, and you don't care about. And essentially that's the end of the game. So run that in a loop, and then once it's finished, the samples are all available in this sampler.flatChain property. So that you can plot their distributions, or plot their tracks, or do whatever other actual science when you're doing examples. Okay, so two other things that I wanted to mention, which is this related module called ACOR that computes the autocorrelation time of the chain. So let me tell you what autocorrelation time is. Others in the audience should speak up, because, again, not the expert. So you saw that in, let's see, in that tuning fork example, we had, so for the Metropolis Hastings one, say, let's just look at that for a second. It was stepping around along the space, taking rather small steps. So if you looked at the position over time, you would see that, so if you plotted its x position with respect to sample number, or like step number, you'd see that this thing sort of drifts around this space, right? And at the end of the day, the samples you want, to be spread around the space and not be correlated with each other. But you sort of can see that these ones are all, so if you looked at just a small set of these ones, you'd only really be covering a small part of you'd only have samples in a small part of the space, because these steps are all correlated with each other. But this would happen if the step size is too small. So if you wanted uncorrelated samples, you'd have to take like every 10th one or something, or every 100th one, and those would be less correlated. So they would be like a more representative or fair sample of the space. So if you can measure, you can essentially take Fourier transform or Fourier spectrum of the position in the parameter space, and that gives you something like a correlation function. So I guess we'll call it autocorrelation, because it's autocorrelation, meaning it's the correlation of the same signal but shifted by some amount of time. So at 0, so this is time difference. So at 0, of course, it's entirely correlated. After one step. So in an ideal world, it would just go like this, right? You would have every sample is entirely uncorrelated with every other sample. But in any sort of practical sampling, you end up that the first sample is pretty highly correlated, the second sample is less correlated, and so on. And it hopefully sort of tails down to some baseline level over time. And where that happens, where it hits a plateau, is kind of a characteristic time. It tells you, so if this were, say, 100, it tells you that sort of roughly after 100 steps, you've forgotten where you started. So those samples are effectively uncorrelated. And that means that if you want a fair sampling, you only really need to keep every 100th sample. However, that means if you want 100 uncorrelated samples, it means you have to run for 100 times 100 steps. So knowing this number is pretty important. Knowing this autocorrelation time is pretty important for understanding what your samples mean or whether you have a good sampling of the space or not. So let's see. This is the autocorrelation time. For this kind of position where it drops to, I don't know exactly how it's formally defined, but I only deal with sketchy ideas of things like and conveniently enough, the primary author of IMC also has this, provides a core module that computes the autocorrelation time for you. So it can tell you at the end of the day what fraction of your samples you should keep or how much you should believe it. So that's a useful thing to have and keep track of. So it'll give you a number like 10 or something, and that means sort of every 10th sample is kind of uncorrelated, and you should keep every 10th sample. Right. Nope. Yeah, and it's certainly a ballpark sort of estimate. Like, so for this example, I computed the autocorrelation for each walker's X and Y positions. And so that gives you like an entire ensemble of guesses of what the autocorrelation time is. And in this example, it gave a mean of like 12 and a standard deviation of 6. So it's really saying, it's only really giving you a ballpark. It's not 100. So, you use it as a guide to say, okay, I should keep like sort of every 10th one or so. It's not rocket science. No, it probably isn't. Right, so okay, good. Thank you. All right, we're nearly at the end, I promise. I wanted to just mention one other handy thing, which is another module by, again, the same author, Daniel Mackie, called Triangle, and it makes these kinds of plots that I'll show you in a second in a very easy way. Oh yeah, so one other thing that I mentioned at the beginning was that it's easy to multi-thread this thing. So am I gonna go back or am I gonna redraw it? Okay, right. So remember how, I'll just redraw it. We said imagine we had 4 walkers exploring a space. And for each of them, at each update step, they need to choose another one, and sample along this line, and decide whether, sample along this line, compute the probability there, and decide whether to take that step. Now, the nice thing is that all 4 of them can do this step in parallel. So that's the part that's really easy to parallelize. So if you had, say, 100 walkers or something, you have to do 100 updates, and you can do them all at the same time. And since I think this computer has 4 cores, maybe 8, the ones you use have, big machines often have 12, 24, so if you want to make things 20 times faster, that's good. And it actually does scale pretty well because assuming the likelihood actually takes some time to compute, then you sort of farm it off to a bunch of cores and do it in parallel. Pretty easy. Here's how to multi-thread it in MC. Threads equals 20. Done. That's one of the reasons this package is popular. That little trick right there. So, okay, so we're at an hour and kind of important. All right, I'm going to push through for a couple more minutes, and then we can take a break. Okay, so I was talking pretty vaguely about a parameter space that has 2 dimensions, that's got an ellipse in it or something. Let's look at a really simple but real example where you might actually want to use Markov-chain Monte Carlo. So imagine this pretty typical case where or this kind of simple case really. You've got a bunch of data points. They have x coordinates that we're going to assume you know perfectly with no uncertainty, and some y measurements with some stated error bars, and you don't necessarily believe them. So imagine like Tully-Fisher relationship or something where one of the things is pretty well measured and the other is not so well measured. So you can imagine that the one is measured, say the x coordinate is measured with certainty and the y is measured with uncertainty. And each of the data points reports some uncertainty. In the paper they say, well, it's 4 plus or minus 0.2. And you'd like to fit a line to it, but you say to yourself, I think that they all understated their error bars, and there's actually some additional error in each of the points. So that's something that's not entirely trivial to assess, just like writing it out with linear algebra. Okay, so how do we write this? How do we deal with it? So we're going to ask about the likelihood of drawing. I don't really like this, the way this is written, so apologies there. So we're going to ask for the likelihood for the y values, the measurements, and the stated, and this doesn't make any sense. Pardon me? Yeah, you're right. The x's and the sigma should be on the right. I'm sorry. So let's, if everybody in your minds move these over to the other side, because those are things that are just given and we're not going to reason about or move about. We'll just treat them as givens. They're just like part of the outside information we have. Okay, so let me try that again. We're going to ask for the likelihoods of the y values given a slope and an intercept and some additional noise that, like, additional noise on the measurements that we believe wasn't, like, is included in the actual samples but wasn't reported. Okay, so they're all Gaussians, and so the y values are drawn from this linear relationship with a variance that's the variance they reported plus this additional thing that we're cheating factor that we're trying to uncover. Okay, so we want to infer those three things, the m, b, and d squared, right? Okay, so taking, yes, and of course, so we need to work, to use MC, we need to switch to log space. So then that first term, the, no, I'm sorry. Yeah, okay. Sorry, I stole these slides, so they're not written the way I would like. So, you know, this is writing out in a way that I don't entirely like. Just the log of that Gaussian that I wrote on the previous page. Like, it's just, let me just write it out. So we want P of the set of y's given MB and delta squared. We said it's a product of Gaussians with a mean of mxi plus b and a variance of sigma I squared plus del squared. So that's got a term, so that's a product, a term that has a what a, I'm going to get this wrong because I'm doing it live, of course, right? It's got what, a square root of 2 pi and a square root of sigma I squared plus delta squared. And then the exponential term, it's just got the minus a half yi minus mxi plus b squared over I squared plus del squared. Okay, so then the term, this term is just this log term, and the chi-squared one is just the log of that term, right? Sorry, that was like this was the worst slide to steal. I should have just written it out myself. So, for being lazy. Okay, so writing it out in, and then, okay. So we have to use MC, we have to give it the full posterior, log posterior, so likelihood and prior. That's the likelihood, and then we've put a prior on d squared that it's strictly between 0 and 1. Because if you look back at the measurements, they were all sort of scattered within that, so it's a pretty reasonable, it's a pretty weak range. And in this example, there is no prior or a flat prior on M and B, which is a terrible idea. And Brendan should skip me again. Okay, so, pardon? Yeah. All right. Yeah, okay. Okay, so here, if this D2 value is outside of the range that you wanted, then we'd have to return a probability of 0. So log of 0, so you just return minus infinity. It will definitely reject those steps because minus infinity is a terrible place to be. This I bar is just the this inverse variance value. Here's the chi-squared computation. So here we're computing this for the arrays of x and y values. So there's a sum over the chi-squared values. Yeah, so then it's just the whole thing is this chi-squared minus this term that has the inverse variances in it. So pretty easy to code up. And so here was, before when I was talking about that triangle plotting code, this is the plot that comes out of that. So this is showing you the samples. Now the labels are hard to read. So this is m at the bottom, b and delta squared. This is b and delta squared. So the ones on the diagonal are showing you the one-dimensional histograms. So the one-dimensional histogram for m. So the slope of this thing is like 1.5 plus or minus 0.1-ish. The intercept is like 3, and the del squared is like 0.2 or something. And then the off-diagonal ones show you the covariance between those two things. So they show you all of the samples, where all of the samples are. And so here's a really classic thing where the slope and the intercept of a line are really anti-correlated. Because you can sort of, if you make it steeper, you have to kind of move it down a bit in order to fit. Yeah, sure. Where to? To the data? Yeah, indeed. Yeah, truly. Right. Okay. Good. Good. Thanks, Brendan. I'll pay you for that comment later. Okay, so the triangle plot is kind of nice in that it lets you look at the one-dimensional histograms to give you some sense of kind of what things are well constrained and what things aren't, and also give you a kind of glimpse of what the correlations are like. Okay, and then here's I think a nice way of communicating your results in this analysis. You saw this earlier with the Comet Holmes stuff, where a nice way of showing your results is to draw a sample, like to take a number of your randomly selected samples and say what they would predict about the data. So here, yeah, it gives at least like some sense of the scatter in the predictions, or like how strongly you constrain what the slopes and things of this line are. And that's all I have. So we should take a break.